In this video, we're going to be looking at how to solve a system of equations that involves a linear function and a quadratic function. We previously talked about how to solve these systems using graphing, and today we're going to talk about how to use the substitution method. We've talked about how to solve a system of equations using substitution in a more conventional system of two lines, but today we're going to talk about doing that with a quadratic function and a linear function. So if you recall, when solving a system of equations, our solutions that we're looking for are represented by a point of intersection. So when you graph the two equations, you have something like this here. So we have this quadratic function and this linear function here. Our solutions are represented by these 2 points here that are the points of intersection. So those are our solutions. So let's go ahead and get into an example where we're given two functions and we want to try and find their solution using substitution. So we want to solve this system of equations using substitution. So we're given y equals the quantity of x minus 3 squared and then x plus y equals 5. So we have an equation for a quadratic in vertex form, which is nice when graphing using transformations, but is not the best for solving using substitution. So we're going to convert this vertex form equation into standard form. So we're going to do that by just expanding this binomial that's being squared. So if you recall, when you have some quantity that's being squared, it just means that it's being multiplied by itself. So we're going to rewrite it so that it's x minus 3 times x minus 3. And then we're going to take each term and distribute it into the second binomial. So we're going to take this x and multiply it into those two terms. So x times x, that's x squared. X times negative 3 is negative 3x. So now we're done with this first term. We've distributed it into both. We're going to go and move on to this negative 3 and distribute the negative 3 into both terms. Negative 3 times x, again, is negative 3x. And negative 3 times negative 3 is positive 9. So we have y equals this. So now we're going to combine our like terms, which we have here, giving us y equals x squared minus 6x plus 9. Now, if you recall, when trying to solve using substitution, we needed one of our equations to have one of its variables isolated. We have that here with this quadratic. So we have this quantity that represents y. And so we're going to take that and substitute it into the y in our other equation. So we have x plus what was y, we're going to replace it with all of that quantity, equals 5. So that quantity is x squared minus 6x plus 9. And this quantity is really being multiplied by like a 1 here. And multiplying this by 1 does not change its value in any way. So really we can just kind of combine like terms. So we have this x that can combine with our negative 6x. So this is like 1 minus 6, so giving us negative 5. So we have x squared minus 5x plus 9 equals 5. And in order to solve this quadratic, there's a couple methods that we can use, but I'm going to subtract this 5, putting this in standard form, and see if it's factorable. So let's subtract 5 from both sides. And I do believe we end up with something that is factorable, which is nice. So we're going to get x squared minus 5x plus 4 equals 0. This is in fact factorable. So we can go through and try and factor this. Remember, we take the leading coefficient, which is 1, and our constant, and we multiply those, giving us 4, and then negative 5. So we're looking for factors of 4 that multiply to negative 5. So when you have a positive product and a negative sum, that tells me we have two negative factors. We have 1 and 4 that work, negative 1 and negative 4, because that multiplies before and adds me negative 5. So now we're going to rewrite this expression using our two new factors to rewrite the middle term and factor by grouping. So we have x squared minus x minus 4x plus 4 equals 0. Split and factor by grouping. So factoring out the GCF from each group, we have an x here, leaving us with x minus 1. And then the leading term is negative, so we're going to factor out a negative, and those have a common factor of 4. And then we have x minus 1 equals 0. Those groups are the same, so that's our first factor. And then what's left on the outside is our second factor. So now to figure out what makes these 0, we're going to use the zero product property. So I'm going to move this over here. So that means just set each factor equal to 0 and then solve those little equations. So adding 1, we get that x equals 1. And then adding 4, we get that x equals 4. Now, if you recall, when we're trying to solve a system, we are looking for a point of intersection. So that means we need both an x and a y. So we already know the x coordinate for both of these. Now we need to find the y coordinates. So we can find the y coordinates by plugging these x values back in to either equation, because if they're a point of intersection, it should be in either of them. So I'm going to plug it into our linear equation because I think it's maybe a little bit easier. So 1 plus y equals 5, and then 4 plus y equals 5, right? So if I subtract 1, I get that y is equal to 4. And if I subtract 4, I get that y is equal to 1. So our two solutions are going to be 1, 4 and 4, 1. So those are our two solutions for this system of equations. For this next problem, I want you to try and solve this system of equations using substitution on your own. It's already nice in standard form, and both of our equations are have our y isolated, so we can pretty nicely just substitute straight in. So go ahead and try this process, and we will come back and talk about it in just a minute. All right, so for this example, we want to solve this equation using substitution. Now, luckily, we already have both of our equations in with one of our variables isolated, and our quadratic is in standard form. So that means I can just take this quantity and substitute it into my other equation to give us what we need. So let's go ahead and do that. So we have x squared plus 11x minus 12 equals 12x plus 30. Again, we want to get this in standard form so that we can hopefully try and factor. So I'm going to subtract 12x from both sides. And while I'm at it, I'm also going to just subtract 30. Again, we're trying to then combine our like terms here. So those cancel to give us 0. And then x squared doesn't combine with anything. 11x minus 12x, that's negative 1x. And then negative 12 minus 30, that's like adding a negative 30. Gives me negative 42. And lucky for us, again, this is factorable. So we're looking for two numbers that multiply to be negative 42, because again, it's 1 times negative 42, so negative 42, and add to negative 1. So the two factors that would do that are going to be negative 7 and positive 6. So let's rewrite this using those two as our middle term. So x squared minus 7x plus 6x minus 42 equals 0, split, and factor by grouping. So common factor here is x, leaving us with x minus 7. This is positive, so we're going to factor out a positive value. 6 goes into both of those, giving us x minus 7 equals 0. So we are left with x minus 7 as our first binomial factor, and x plus 6 as our second binomial factor. So using the zero product property, take both of these factors and set them equal to 0. X minus 7 equals 0, and then x minus 6 equals 0. Solve these, so, whoops, that should be x plus 6. Add 7, so we get that x equals 7, and then subtract 6 so that we get x equals negative 6. So our first solution is going to have an x coordinate of 7, and we need to figure out the y coordinate. And our second solution is going to have an x coordinate of negative 6, and again, we need to find the y coordinate. So let's take 7 and plug it in. Again, I'm going to plug it into my linear equation because I just think it's a little easier. So it's y equals 12 times 7 plus 30. 12 times 7, that's 84. 84 plus 30, that's going to be 114. So my y coordinate is going to be 114. And then 12 times negative 6, that's going to be negative 72. Negative 72 plus 30 is negative 42, and that's my y coordinate for my other point of intersection. So these 2 points are our solutions. They represent our points of intersection if we were to graph these two functions.